This video is being provided just in case we don't finish or someone's absent, but it's going to go a little bit more in depth as to what this number e is. We've previously said that we have kind of three basic logs. We have a log base 2 of a number, which can be abbreviated as the LB of 2 or the binary log of 2. We have the log base 10 of a number, which can be abbreviated as log of the number, also called the common log. And today we talk about the log base e of x, which can also be abbreviated the natural log of x. Now, e itself is a number that has a value of approximately 2.71. It is irrational, which is very much like other irrational numbers we have, but it is also transcendental. And I would challenge you, there's a great video, YouTube video on number file. If you look up the number file transcendental video, it's not terribly long, it's kind of fun to watch, but they get really nerded out and excited about transcendental numbers. Basically, there's numbers that can't be a solution to a quadratic equation. And if you think about it, you really can't get pi as a solution with regular integer coefficients. Meaning I couldn't take something like 2x squared plus 7x plus 1 equals 0 and get anything other than square roots of numbers. And I'll get square roots of numbers or I'll just get perfect numbers. But transcendental numbers don't do that. E is like that and pi is like that, and there's a very important relationship between e and pi. So why 2.71? Where did that come from? I'm going to give you three answers to that question, and there are more than three. I might actually even give you four. Here's one of them. If I graph the reciprocal function y is equal to 1 over x, and I start putting points down, 1, 1, 2, 1/2, 3, 1/3, 4, 1/4, and then 1/2, 2, 1/3, 3, this is what the function's going to look like. And similarly, in the negative regions, we're going to have something very similar. -1, -1, -1/2, -2, -2, -1/2, and it would just keep going like that. You can see a symmetry with this, and you could do a t-chart to plot this. You can also plot this in your graphing calculator, but that's a very good representation of y is equal to 1 over x. Now, we previously talked about having this number line from 0 to infinity, where the midway point is now 1. So if I look at this graph and I wanted to find the area under the curve, if I kind of look and shade this starting at 1, and I wanted this area to be equal to 1, I would actually shave up to this number right here, and that number is e. And this gives me an area equal to 1. Now, why is that important? That's going to come much, much later. Let me give you another one. Let's go right here. Let's graph this line. This is going to be y equals e to the x. And if I graph that, I know that I have a y-intercept of 1, and I know that if I go plug in 1, I'm going to get e, and if I plug in -1, I'm going to get 1 over e. Well, we can just kind of guesstimate this. We're going to have basically a curve that looks like this, much like most, sorry, it's kind of hard to draw those, but sort of like most exponential functions. It's a little bit more broad than that. But anyway, one of the neat things about this graph is that if I actually